According to National Electrical Code Section 240.4d, a 15 amp receptacle is permitted to be installed on a 20 amp circuit. Also, according to National Electrical Code Section 210.19a, a number 14 American wire gauge wire is permitted for use on a 15 amp branch circuit. Therefore, it is permissible to use number 14 American wire gauge pigtails to connect 15 amp receptacles to a 20 amp branch circuit. Let's delve deeper into the specifics of these code sections and their implications for electrical installations. National Electrical Code Section 240.4d addresses the protection of flexible cords and fixture wires. It outlines the conditions under which these conductors are allowed to be protected by overcurrent devices exceeding their ampacities. This section is crucial for understanding when smaller conductors, like those found in flexible cords or fixture wires, can be safely used in circuits with higher ampacity ratings. The rationale behind this allowance lies in the limited length and specific application of these conductors. Flexible cords and fixture wires are typically used to connect portable appliances or lighting fixtures to a branch circuit. Their short length and the inherent protection provided by the appliance or fixture itself reduce the risk of overheating or fire, even when protected by a high-rated overcurrent device. For instance, a lamp cord connected to a 15 amp receptacle on a 20 amp circuit is generally acceptable under this rule. The lamp itself provides additional protection, and the cord's short length minimizes the potential for a fault to escalate into a dangerous situation. However, it is essential to adhere to the specific requirements and limitations outlined in National Electrical Code Section 240.4d to ensure safety. These requirements may include restrictions on the type of conductor, the length of the cord or wire, and the type of appliance or fixture being connected. Furthermore, local codes or regulations may impose additional restrictions or requirements, so it is always advisable to consult with a qualified electrical inspector or engineer before undertaking any electrical work. Now, let's turn our attention to National Electrical Code Section 210.19a, which deals with the ampacity of branch circuit conductors. This section specifies the minimum size of conductors required for branch circuits based on the rating of the overcurrent device protecting the circuit. In general, the conductors must have an ampacity equal to or greater in the rating of the overcurrent device. For example, a 20 amp branch circuit typically requires number 12 American wire gauge copper conductors, which have an ampacity of 20 amps under normal conditions. However, National Electrical Code Section 210.19 also includes exceptions that allow for the use of smaller conductors in certain circumstances. One such exception, as mentioned earlier, permits the use of number 14 American wire gauge conductors on a 15 amp branch circuit. This exception is based on the understanding that number 14 American wire gauge conductors have an ampacity of 15 amps, which is sufficient for a 15 amp circuit. Another relevant consideration is the use of pigtails. A pigtail is a short length of wire used to connect multiple conductors to a single terminal or device. Pigtails are commonly used in receptacle boxes to connect the incoming branch circuit conductors to the receptacle terminals. When using pigtails, it is essential to ensure that the pigtails are properly sized and installed to prevent overheating or loose connections. In the specific scenario you described, where number 14 American wire gauge pigtails are used to connect 15 amp receptacles to a 20 amp branch circuit, the use of number 14 American wire gauge pigtails is permissible because number 14 American wire gauge conductors are rated for 15 amps, and the receptacles being connected are also rated for 15 amps. The 20 amp of a current device protecting the branch circuit will trip in the event of a fault or overload, preventing damage to the number 14 American wire gauge pigtails or the receptacles. However, it is crucial to ensure that the number 14 American wire gauge pigtails are properly connected and that the connections are secure. Loose connections can create resistance, which can lead to overheating and potentially cause a fire. Furthermore, it is essential to use appropriate wiring methods and materials for the installation. The wiring must be installed in accordance with the National Electrical Code and any applicable local codes or regulations. This includes using approved boxes, connectors, and wiring methods, as well as properly grounding the circuit. In summary, the use of number 14 American wire gauge pigtails to connect 15 amp receptacles to a 20 amp branch circuit is permissible under the National Electrical Code, provided that the installation meets all applicable requirements and that the connections are properly made. It is always advisable to consult with a qualified electrician or electrical inspector to ensure that the installation is safe and compliant with all applicable codes and regulations. To further clarify the requirements for conductor ampacity, let's discuss National Electrical Code Section 310.15, which provides tables for determining the allowable ampacities of insulated conductors. These tables take into account various factors such as the type of conductor, the insulation temperature rating, the ambient temperature, and the number of conductors in a raceway or cable. The allowable ampacity of a conductor is the maximum current, in amps, that the conductor can carry continuously under specific conditions without exceeding its temperature rating. Exceeding the temperature rating of a conductor can damage the insulation, leading to short circuits, ground faults, and potentially fires. Therefore, it is essential to select conductors with an ampacity that is sufficient for the load they will be carrying. The National Electrical Code tables provide guidance on selecting the appropriate conductor size for various applications. For example, Table 310.15b16 lists the allowable ampacities of insulated conductors rated up to 600 volts based on the conductor's size, insulation type, and ambient temperature. This table shows that number 14 American wire gauge copper conductors with a typical insulation type, such as THHN or THWN, have an ampacity of 15 amps when installed in a raceway or cable with no more than 3 current-carrying conductors. Number 12 American wire gauge copper conductors, on the other hand, have an ampacity of 20 amps under the same conditions. These ampacity values are based on a maximum conductor temperature of 75 degrees Celsius. It is important to note that the allowable ampacity of a conductor may need to be adjusted based on the ambient temperature and the number of conductors in a raceway or cable. If the ambient temperature is higher than 30 degrees Celsius, the ampacity must be derated to account for the increased heat. Similarly, if there are more than 3 current-carrying conductors in a raceway or cable, the ampacity must be derated to account for the increased heat generated by the conductors. The National Electrical Code provides tables and formulas for calculating these derating factors. In addition to ampacity, it is also important to consider the voltage drop in a circuit. Voltage drop is the decrease in voltage that occurs along the length of a conductor due to the conductor's resistance. Excessive voltage drop can cause appliances and equipment to operate inefficiently or even malfunction. The National Electrical Code recommends that voltage drop be limited to a maximum of 3% for branch circuits and 5% for feeders. To minimize voltage drop, it is important to select conductors that are large enough to carry the load without excessive voltage drop. The longer the circuit and the higher the current, the larger the conductors need to be. There are various online calculators and software programs that can be used to calculate voltage drop in a circuit. These tools take into account a conductor's size, length, current, and voltage to determine the voltage drop. By carefully considering ampacity, voltage drop, and other factors, it is possible to design electrical circuits that are safe, efficient, and compliant with the National Electrical Code. Remember, electrical work can be dangerous, and it is always advisable to consult with a qualified electrician or electrical inspector before undertaking any electrical work. They can provide expert guidance and ensure that the installation is safe and compliant with all applicable codes and regulations. Furthermore, it is crucial to stay up to date with the latest edition of the National Electrical Code, as the code is revised every 3 years to reflect new technologies and best practices. By staying informed and following the code, you can help to ensure the safety and reliability of electrical installations. To reiterate, while using number 14 American wire gauge pigtails on a 20 amp circuit feeding 15 amp receptacles is generally permissible according to the National Electrical Code under specific conditions, it is paramount to prioritize safety and code compliance. Always verify local regulations and consult with qualified professionals for any electrical work. Safe electrical practices are not just about following rules, but also by understanding the underlying principles that ensure the safety of people and property. The National Electrical Code is a comprehensive set of guidelines designed to minimize electrical hazards, and it is essential for anyone working with electricity to be familiar with its provisions. By adhering to the code and seeking expert guidance when needed, you can help to create a safer electrical environment for yourself and others. Always remember to de-energize circuits before working on them, use appropriate personal protective equipment, and follow proper wiring methods. Electricity is a powerful force, and it must be treated with respect. Let's also discuss the importance of proper grounding and bonding in electrical systems. Grounding and bonding are essential for providing a safe path for fault current to return to the source, which helps to trip the overcurrent device and clear the fault. Grounding involves connecting the electrical system to the earth, while bonding involves connecting all metal parts of the electrical system together. The National Electrical Code specifies the requirements for grounding and bonding in detail. It covers topics such as the size of grounding and bonding conductors, the methods of making grounding and bonding connections, and the types of equipment that must be grounded and bonded. Proper grounding and bonding are crucial for preventing electrical shock hazards and minimizing the risk of fire. When a fault occurs in an electrical system, such as a short circuit or a ground fault, the fault current will flow through the grounding and bonding system back to the source. If the grounding and bonding system is properly installed, the fault current will be high enough to trip the overcurrent device, such as a circuit breaker or fuse, which will de-energize the circuit and clear the fault. However, if the grounding and bonding system is not properly installed, the fault current may not be high enough to trip the overcurrent device, which can lead to a dangerous situation. In this case, the metal parts of the electrical system may become energized, posing a shock hazard to anyone who comes into contact with them. Furthermore, the fault current can cause overheating and potentially a fire. Therefore, it is essential to ensure that the grounding and bonding system is properly installed and maintained. This includes using the correct size of grounding and bonding conductors, making secure connections, and regularly inspecting the system for any signs of damage or corrosion. The National Electrical Code also requires that ground fault circuit interrupters, or GFCIs, be installed in certain locations to protect against electrical shock hazards. GFCIs are devices that monitor the current flowing in a circuit and detect any imbalances that may indicate a ground fault. If a ground fault is detected, the GFCI will trip the circuit, cutting off the power and preventing an electrical shock. GFCIs are typically required in bathrooms, kitchens, and outdoor locations where there is a higher risk of electrical shock. They are an important safety device that can help to protect people from serious injury or death. So, as we conclude, remember that electrical safety is everyone's responsibility. By understanding the principles of electricity, following the National Electrical Code, and seeking expert guidance when needed, you can help to create a safer electrical environment for yourself and others. Always prioritize safety and never take shortcuts when it comes to electrical work.